Hello, my name is Girastia Lintang Desnova. I'm from Class B. My NEM are 220-301-201-40117. First, I would like to thank Mr. Ayustaning Fitriono for giving me the opportunity to present my work. So, I'm going to presenting a PowerPoint about insect for bakery goods. In these topics, they are including first, introductions about why insect. Second one was materials and methods about how insect turns into bakery goods. The third one was results and discussion about how it will be. The fourth one was conclusions. Is it useful and beneficial? Now we're moving into the first one, introduction. Considering the rising population worldwide and the increasing demand for additional sources of proteins, insects are seen as an economical alternative. Entomophagy, the eating of insects, has been part of the world habits for centuries. Only recently, it has gained interest in Western countries. A main advantage of insects is that they have high food and feed conversion efficiency, and their feed can be limited to industrial byproducts and cereal grains. In Europe, certain insect species are reckoned for partial replacement of conventional sources of animal proteins in food and feed. Despite the sustainable benefits, Western consumers could be reluctant to accept insects as a legitimate protein source because they have never played a significant role in their food culture. The most commonly eaten insects are members of Hemiptera or cicadas, leaf and plant hoppers, true bugs, scale insects. And then the second one was Odonata, or as known as dragonflies. And then the third one was Lepidoptera, or as known as caterpillars of butterflies and moths. And then the fourth one was Orthoptera, or as known as grasshopper, locust, crickets. And then the fifth one was mealworms. And then the sixth one was Coleoptera, or as known as beetles. And then the seventh one was Hymenoptera, or as known as bees, wasps, and ants. And then the last one was crickets. Why insects? The production of particular insects is more sustainable than conventional sources of proteins, considering water use and greenhouse gas emissions. Certain insect species could be targeted for being incorporated as a powder in food products, providing additional nutrients. Insects are richer in proteins than beans. It's about 23.5%. Lentils about 26.7%, or soybean about 41.1%. It has been reported that insects contain around 35 until 61%, 15 until 40%, and 3 until 10% of proteins, fat, and minerals, respectively. Now we're moving into the second one. It was materials and methods. A. Materials. Commercial bread-making flour was supplied by Harinera La Meta in Barcelona, Spain. Salt and compressed yeast was purchased from the local market. Hermetia illucans larvae were provided by Bioflytech in Alicante, Spain. Acheta domestica, or house cricket flour, and mealworm beetle, Tenebrio molitor, were provided by Insecticide in Alicante, Spain. Some adults of Acheta domestica were also provided for the morphological characterization. Larva samples were frozen at -40 degrees Celsius and freeze-dried in Virtis genesis 35 EL under vacuum condition of 8 M-bar. Then they were milled in an ICA M20. The powder was kept at -20°C until used. B. Insect characterization, morphology, and composition. Proximate analysis of insect, wet flower, and bread samples was determined according to the ACC International 2012 standard procedures. Analysis including moisture, ash, fat, crude protein, and dietary fiber. Non-protein nitrogen was determined after precipitating the proteins with TCA, and then evaluated using the Joule method. Carbohydrates were determined by difference and expressed as percentage. Briefly, method involved two important steps: demineralization and deproteinization. C. Demineralization and deproteinization. First, demineralization. In order to remove cuticles, samples were treated with 1 mole HCl at 85 until 90°C for 50 minutes under constant stirring. The ratio of raw sample to acid solution during the extraction was 1:20. Then, it was centrifuged at 3000 grams for 5 minutes and washed with distilled water to remove the excess of HCl. Second one was deproteinization. Sediment from the previous step was suspended 1:20 in alkali and kept at 85 until 90°C for 35 minutes under constant stirring to remove proteins completely. The mixture was vacuum filtrated in a butcher funnel with filter paper. Washed several times with deionized water to remove the excess of NaOH, and then dried in an oven at 100°C overnight. The residue obtained was designed and as a purified insect chitin in the form of a very light brown powder and calculated by weight. And then we're moving into point number 3, called results and discussion. A. Insect morphology and proximate composition. Edible insects used as a source of proteins to fortify breads were morphologically and chemically characterized. Insect flowers showed a more complete and rich nutritional profile than the wheat flowers, with exception of carbohydrates. Flowers from insects were rich in protein followed by fat. The content of NPN in the present study agrees with the values of chitin nitrogen. The barely differences in the chitin content of the three flowers, regardless their development state, might be ascribed to the type of insect and taxonomy differences. Area, width, and height were measured. H. elegans and Timolidor were used as larva stage, while A. domestica was in adult stage. As it was expected, A. domestica, commonly known as house crickets, had the greatest area compared to the larvae from H. elegans and T. molitor or mealworm. Larvae from H. elegans showed a golden brown exoskeleton that curls into a C shape, which was 13.79 mm long and 3.86 mm thick. Larvae from Timolidor displayed a darkened color with a yellowish-brown shell that measures. A. domestica showed a brown-black color with a size around 19.12 mm length and 3.86 mm width. Proximate composition expressed in dry basis of wheat flour and the resulting flour after insect grinding is summarized in Table 1. Insect flour showed a more complete and rich nutritional profile than the wheat flour, with exception of carbohydrates. Flour from insects were rich in proteins followed by fat. However, there were significant differences among insects, especially for flower from A. domestica had the highest content of proteins, and H. elegans flower had the biggest fat content. Flowers from larvae showed a carbohydrates content that ranged between 14.84% and 16.24%, and the A. domestica in adult state had lower content of carbohydrates. Components like carbohydrates are frequently referred as nitrogen-free extract. Non-protein nitrogen in insect is related to the presence of cysteine, nucleic acid, phospholipid, and extraction products in the intestinal tract. B. Breads enriched with insect flowers. Breads containing insect flowers showed similar appearance than control bread, with exception of crumb color, which showed different brownish intensities. The addition of insect flour didn't impair dough fermentation, obtaining breads with acceptable volume and open crumbs. Nonetheless, the bread containing H. elusens exhibited a more close crumb and lower volume. It must be stressed that during baking of breads containing H. elusens flour, some of flavors were released, likely due to its fat composition. Generally, the quantities of food flour are associated more closely with lipids, mainly unsaturated lipids, than with proteins and carbohydrates. No significant differences were found between the texture parameters obtained for A. domestica and T. molitor containing breads. Again, although the high amount of fat in H. elusens could be the cause of the texture results, breads made with the fatted flour had similar texture parameters, with the exception of hardness and chewiness, bringing about softer crumbs. Therefore, the composition of H. elusens flour, likely regarding proteins and carbohydrates, might be responsible for interfering in the proper development of the dough during the fermentation, provoking poor gas retention, ability of resulting weak gluten networks, yielding a tight structure of breadcrumbs. The color of insect flowers was measured to find possible correlation with crumbs color. The addition of insect flour affected the nutritional composition of breads. Breads containing A. domestica flour showed the highest content of proteins, which was expected since it had the major percentage in flour. All insect flours provided IDF and SDF, although their contribution to the soluble digestible fiber fraction was more noticeable. There was a marked difference in IDF in the sample containing T. molitor comparing with the rest sample. However, results obtained in the present study show the alternative of insect to be used as ingredients and baked goods. Now, finally, we're on the last part of my presentation, which is conclusion. Edible insects in the form of flour could be incorporated in baked goods to improve their nutritional pattern, principally regarding protein content. Among the insects tested, A. domestica was the one that led to breads with technological features similar to wet breads, but improved nutritionally regarding proteins and fiber content. Overall, results confirm the usefulness of insect flour for protein enrichment of bread. And that's it. I hope with this presentation, it can add insight to those who read and listen. Thank you so much for your attention. Bye.